Hello friends, welcome back my YouTube channel MS Maths. In this video, we are going to discuss about the solution of ordinary differential equation by using Laplace transform. If you want to know about the concept, what is the concept of the ODE and what is the concept of the ODE solution by using Laplace transform, and I have discussed about this topic in our previous videos. Now in this video, we are going to discuss another type of differential equation which we will discuss the solution of the differential equation by using the by using the Laplace transform. Now what is the difference between that type of ODE and the which ODE we will solve in this video? Basically in this video we will discuss particular this type means if the variable are there multiply with the derivative terms or a function in a differential equation, then how can we solve by using the Laplace transform? That type of differential equation we are going to discuss in this particular video. Okay, so basically this particular type of differential equation is known as the Cauchy-Euler, and where t is a variable and Laplace of function ft is nothing but fs bar. We are denoting this value. So basically this is Cauchy-Euler differential equation. Then you can also find the solution of the Cauchy-Euler differential equation, but there is it is not necessary there will be t square with y double dash and t with y dash. No, it is not necessary. Like t cube is also there, t power 1 is also there. Okay, we will solve like this type of AD. Like you can see here, y double dash is in multiple with the t power 1, not t square. But I am going to discuss this particular this particular type, so that it can be generalized. Okay, so now what will we use? We will use this theorem of the Laplace transform. What is this theorem? Like whenever the t power m or t power whatever the value of the t power, then the Laplace of that is nothing but minus 1 power m d power n, and it means the what will be the power of the t, and we will identify and then differentiate with respect to x m times, m is the power of the t. Okay, and then we will differentiate this term, the Laplace of that yt, that function, the Laplace function, Laplace transform of that yt, and we will differentiate m times that. Okay, m times that Laplace. Now we know about that what is the value of this y dash and what is the Laplace, and first step is nothing but the taking Laplace both side. Now I am writing the first step, taking Laplace transform both side. So what will be the Laplace? Laplace transform of t square y double dash plus t Laplace transform of t y dash and Laplace of y and Laplace of f of t, and we have considered that Laplace of f of t is nothing but f as y bar, and also we can consider Laplace of yt is nothing but y bar s, and we can also write it as y bar only. Okay, now we are going to discuss first of all what will be the value of this one. Here t power 2, it means minus 1 power 2 and d2 by ds square y double dash, Laplace of y double dash, that is nothing but s square y bar minus s y 0 minus y dash 0. Okay, this is the format, and this is another theorem of the differential, Laplace transform of the differential, Laplace transform of the derivatives. Okay, and this is the derivatives Laplace transform, and then this is the format of the the value of this y double dash we have discussed in our previous video. Okay, now next thing is here t power 1, it means minus 1 power 1 d by ds only one times. Here we are going to derivative with respect to 1, but here only power 1, and then the value of this is nothing but s y bar only, and minus s there is no s, there is only y 0, and then after that this is nothing but y bar, and also this is fs bar. Okay, so this will be the solution for this differential equation. Now we have to we will put the initial values which we will give in whatever will be given in the equations or in question we will put here, and then differentiating, and then we will get a ODE, ordinary differential equation, and then solve this, and you can easily solve by using this. And after that, free, what will be the term? Free the y bar and take Laplace inverse. Take Laplace inverse of y bar, then you will get the required solution. you will get the required solution in terms of y. So now we are going to discuss one question. We have a question, we have a ODE. This is nothing but t y double dash plus y dash plus t y equals to 0. You can see here there is an uncertainty in a power t power, like this is not like it is not necessary there is only t square, and I'm going to discuss like this is nothing but a Cauchy-Euler equation, but this is not Cauchy-Euler equation, but it is a variable coefficient differential. Like we can generalize this by using the variable. I can say this is nothing but a variable coefficient OD. Okay, variable coefficient OD. Okay, now here this is the initial value we have put in this value. Now, okay, no problem. Basically, first of all, this is equation number 1. So what will be our first term, that they are taking Laplace transform both sides. So on taking Laplace transform, t y double dash Laplace of y dash Laplace of ty is equals to 0. Right hand side is 0. Okay, no problem. Now the Laplace, here is a t power 1, it means minus 1 power 1 d by ds only, one time derivative, and the value of this is nothing but s square. You can see here s square y bar. Yeah, you can write here, let Laplace of y is nothing but y bar and minus sy0 minus y dash 0. Okay, this is the term for the value of the y dash. And now after this we will put here y Laplace of this one. This one is nothing but, like if there is no multiple in a t, then we can write simply this y bar minus y0, and the Laplace of this one. Now here is also t in multiple and one time multiple, then we will use minus 1 power 1 d by ds, and the Laplace of this is nothing but y bar ds, and it is equals to 0. Now we will solve this thing, minus 1. So first of all we will put this value. So this is nothing but 1. So s square y, here is d by ds minus s, and minus, like we have not this value, so we will consider let y dash 0 is equals to a, something constant. Okay, it is nothing but a constant which we will derive, that will be 0. Okay, and now this will be the s y bar minus y0, it is nothing but 1. Okay, we have the initial values, this is 1 also, and now it is dy bar s ds is equals to 0. Now we will differentiate. Okay, this is y bar, we will differentiate with respect to s. Remember, y bar is also a function of t. It means y bar is a function of s, then y bar is also differentiated like this term. So here we will use the u into v formula. So minus, on putting the derivative here, this will be 2 y bar s. Firstly we will differentiate s square, and then plus s square dy bar over ds minus s, it is 1. Okay, and next term we will get plus sy bar minus 1, and this is nothing but y bar over ds is equals to 0. So here it is nothing but 2s y bar minus of s square dy bar over ds, and it is plus 1, and it will be 0. Okay, it will be 0. I am not writing here. Okay, it will be 0. So it is plus 1, and now this is plus s y bar minus 1 minus dy bar ds equals to 0. This one and this one got cancelled, and also we can take common dy bar over ds as, like we can take minus common also, then this is s square plus 1, and it is minus of 2s y bar. Okay, plus this, and it is nothing but minus 2 plus 1, it is minus, and it is 0. So now we can write as taking minus common, and we can write this is nothing but y bar ds s square plus 1 plus y bar or s y bar equals to 0, taking minus common, and okay, multiply minus both sides. Now this will be a linear differential equation, ordinary linear differential equation, and we can easily solve this by using dy bar ds is equals to, by taking this part right hand side, it is nothing but minus as y bar over s square plus 1. Now we can solve this, like we can integrate both side, apply integration both side. This, okay, apply integration both side, or oh sorry, for that variable separate. First of all, we have to separate the variable like this, dy bar over d, and now we'll put the integration here, minus s over s square plus 1 ds. Consider this s square plus 1 like t, oh not a t, like t is in a differential equation like m, then 2s ds, 2s ds is equals to dm, then it is nothing but log of y bar, and this will be minus 1 by 2 log of s square plus 1 and another constant c. Okay, I'm writing another constant c, like log of y bar plus 1 by 2 log of s square plus 1 is c. Now we can apply the property of the log, so log of root of s square plus 1 is equals to c. And now here we can solve easily. This is nothing but y bar over root of s square plus, oh sorry for that, not dividing, y bar into root of s square plus 1 is equals to, or we can write here like c is in a log term. Okay, so it will be easy for us, like taking anti-log here, then y bar is nothing but c over root of s square plus 1. Now taking, like this is the y bar, I am writing here the free y bar and solve this, and after that taking the Laplace inverse. Now taking Laplace inverse, so it is nothing but y, and the value of this is nothing but 1 upon root of s square plus 1. Laplace inverse is nothing but Bessel's function, it is nothing but Bessel's function, so c into Bessel's function. Okay, and also if we have some another IVP or some another condition, we can easily calculate the value of this one, or you can if we have this one, y0 is equals to 1 when t is equals to 0, it means Bessel's of t is nothing but 1, oh sorry, Bessel's of 0, Bessel function, like this is the property of Bessel function, it is nothing but 1, and we will put 1 here. So we get by using IVP, this is nothing but 1c into 1c is equals to 1. It means our complete solution is nothing but this. This is our complete solution, which we will which we have got by using the Laplace transform. So this is all about the solution of the ODE by using the Laplace transform, which the variable coefficients is in the the variables function, or like variables in a multiple of the derivative terms or derivative. So thanks for watching my video. Keep watching MS Maths, and in this video we have discussed all the concepts. So thanks for watching this video, and subscribe the channel, like the channel, share the video, and support us. Thank you. Bye bye.